single-phase induction motor with split phase. How does a rotating magnetic field form in a single-phase induction motor? What are the differences between single capacitor and dual capacitor motors? If you're curious to find out, stay tuned until the end. The construction of a single-phase induction motor is quite similar to that of a squirrel cage, three-phase induction motor. However, the stator in a single-phase motor has two windings, the main winding and the auxiliary winding. When a single-phase AC power source is applied to the stator windings, a magnetic field is produced, causing the motor to rotate at a speed slightly below the synchronous speed. The rotor's design is similar to that of a squirrel cage three-phase motor. Types of single-phase split-phase. Induction motors. Motors with a running capacitor. Motors with both a running and a starting capacitor. Motors without a capacitor. As mentioned earlier, these motors have two windings, the auxiliary winding and the main winding. The main winding alone cannot create a rotating magnetic field, which means it cannot generate starting torque. That's where the auxiliary winding comes in. In the image, you can see the torque speed characteristics for each type of motor. Adding a capacitor improves the starting torque of the motor. Now let's look at how the capacitors are connected. In a single capacitor motor, the capacitor is connected in series with the auxiliary winding. To reverse the motor's direction, simply switch the polarity of either the main or auxiliary winding. Keep in mind that the terminal boxes of single-phase induction motors vary greatly. To properly wire any motor, carefully follow the connections of the windings and capacitors. In a motor with two capacitors, one acts as the running capacitor and the other as the start capacitor. The starting capacitor typically has a much higher capacitance. Once the motor reaches its rated speed, the start capacitor must be disconnected from the circuit, usually via a centrifugal switch. A centrifugal switch is an electromechanical device that operates based on the principle of centrifugal force. The decision to use one or two capacitors depends on the motor's design. Motors with two capacitors provide higher starting torque and are suitable for heavier applications. Some single-phase induction motors have no capacitors at all and rely solely on the auxiliary winding for startup. These motors are typically designed for specific, lightweight applications. In some single-phase induction motors, a centrifugal switch is wired in series with the auxiliary winding. Once the motor attains its nominal speed, the centrifugal switch disengages the auxiliary winding. Subsequently, the main winding generates a pulsating magnetic field. Nevertheless, due to double revolving field theory of single-phase induction motor, the motor can produce torque. Analyzing the rotating magnetic field. The main and auxiliary windings are distributed across the stator and are physically 90 degrees apart. The current passing through each winding generates its own magnetic field. You can see the magnetic fields produced by the main winding and the auxiliary winding. Individually, these fields are pulsating, not rotating. Now let's examine the resultant vector. If the currents in both windings are in phase, the resultant is also pulsating, with no rotation. If there's a phase difference between the winding currents, the resultant becomes a rotating magnetic field. To understand this more precisely, observe the input voltage, main winding current, and auxiliary winding current. The main winding, with more turns and thicker wires, has high inductance and low resistance, causing a significant phase lag with the input voltage. The auxiliary winding, with fewer turns and thinner wires, has lower inductance and higher resistance, resulting in a smaller phase lag. The current vectors are drawn approximately and may slightly change with variations in the motor's load. Transient states of the currents have also been ignored. The vectors and curves you see are designed to help better understand the rotating magnetic field. Notice how the phase shift of the auxiliary winding current affects the rotating magnetic field. This very change encourages designers to use a capacitor in single-phase induction motors. Note that the phase difference between the current and input voltage also depends on the motor's mechanical load. Without a capacitor, the rotating magnetic field is weak, and the motor has very low starting torque. Motor with a running capacitor. In this configuration, the phase difference between the currents increases, and the auxiliary winding current amplitude is higher. This improves starting torque and ensures smoother torque production during continuous operation. Efficiency and power factor also improve. A 90 degrees phase difference between the winding currents makes the motor operate similarly to a balanced two-phase motor, improving its performance. Keep in mind that in this state, if the motor load is less than its rated value, the phase difference between the currents will exceed 90 degrees. Also note that the capacitor voltage in a motor with a 230-volt input can rise as high as 380 volts. This voltage increase usually happens when the motor load is low, indicating resonance between the windings and the capacitor. A practical example for a 2-horsepower single-phase induction motor shows how much the capacitor voltage can rise. Motor with 2 capacitors. One capacitor acts as the start capacitor and must be disconnected once the motor reaches its rated speed. The start capacitor increases the current amplitude in the auxiliary winding. Although the phase difference between the currents exceeds 90 degrees, it helps the motor achieve better starting torque and provides the reactive power needed for improved startup performance. Once the start capacitor is disconnected, only the permanent capacitor remains in the circuit. The start and running capacitors are designed differently, with the start capacitor being larger in size. Motors with 2 capacitors generally have better performance, higher efficiency, and a longer lifespan. Here is a summary for all types. If you found this video helpful, don't forget to like, share, and subscribe for more engaging explanations on electrical engineering concepts. Thank you for watching, and see you in the next video.